So now formally we are going to start. Good evening. Good evening, ladies and gentlemen. After the success of first edition, we are excited to begin the second innings of PER lecture series. Indian Association of Physics Teachers has always been committed to promoting excellence in physics teaching and learning, and this initiative is another step in that direction. I welcome you all to this online lecture series. Physics education research is an important field that studies how students learn physics and how teachers can make physics teaching more effective and engaging. PER helps us move beyond traditional teaching methods and adopt research-based practices that improve conceptual understanding, critical thinking, and scientific temperament among students. Today, when education is rapidly evolving with technology and new learning environments, PER plays a crucial role in shaping the future of physics learning, teaching, and inspiring the next generations of learners. We began this journey of online lecture series in 2023, and the first series continued successfully for almost 18 months. During that period, we had the privilege of hosting many renowned physicists from different institutes, national and international institutes, who delivered inspiring and thought-provoking lectures. This includes Nobel laureate Professor Paul Wyman, Professor David Sokolov, and Professor Chandralekha Singh, Professor Arvind Kumar, Professor Vijay Singh, and many more. And after a gap of nearly 1 year, we are delighted to restart this lecture series with the new enthusiasm and fresh energy, with the aim of understanding and discussing the latest developments taking place in the field of PER. On behalf of IAPT RC23 Himachal Pradesh, I warmly welcome all the participants, speaker, and distinguished guests joining us today. First of all, I extend my heartfelt welcome to the chief guest of today's program, our worthy National President of IAPT, Professor P.K. Ahluwalia, who has truly been the driving force behind this initiative. His continuous encouragement and inspiring leadership have motivated us to undertake initiatives like this. We are deeply grateful for his constant guidance and support. I also extend my heartfelt welcome to Professor Anvesh Mazumdar, who has kindly agreed to chair today's session. Professor Anvesh Mazumdar, a distinguished academician, researcher, and educator whose contributions to physics education research and science education are widely recognized and deeply appreciated. I welcome you, sir. I warmly welcome Ms. Rekha Ghorpade, the General Secretary of IAPT, whose dedication and commitment continue to strengthen the activities and vision of the association. I warmly welcome our senior professor, Professor Ghatak, um, for joining us and motivating us today. I extend my sincere gratitude and welcome to Professor Kuldeep Sharma, President of IAPT RC23 Himachal Pradesh, for his constant support, guidance, and encouragement in organizing such meaningful academic program. A very special welcome to speaker of the first lecture of this new series, Ms. Jaya Kashyap. The topic of our talk is Students' Sense Making During Physics Problem Solving, a Case Study. We eagerly look forward to an engaging, insightful, and enriching session with her. Once again, I warmly welcome all the professors, teachers, researchers, and students who have joined us today. I wish everyone a wonderful and intellectually stimulating lecture series ahead. So now I would like to invite President of IAPT RC23, Professor Kuldeep, to say a few words regarding this the series and IAPT RC23.
Namaskar, ma'am. Thank you.
Namaskar, sir.
Namaskar, sabko. Uh, Good evening.
Good evening, sir.
On behalf of IEPT RC23, I also welcome you all to the inaugural lecture 1 of this PER online lecture series 2026. I would also like to welcome chief guest of the today's webinar, Professor P.K. Ahluwalia, who is the motivating force and keep on encouraging us to do such events regularly. And I also extend my heartfelt welcome to chairperson of today's this lecture, Professor Anvesh Majumdar, TIFR Mumbai. And I extend hearty welcome to our speaker, eminent speaker, Ms. Jaya Shivangi Kashyap, Department of Physics and Astronomy, University of Petersburg, who will be delivering the expert talk on student sense making during physics problem solving. And we are really honored to have you, madam, today with us and all of our participants, respected participants. I extend our heartfelt welcome to Professor Rekha Gorpade, madam, uh, General Secretary of IAPT, and Dr. Sapna Sharma also. I extend our welcome to teachers, students to this webinar, and special uh, thanks to Professor Ghatak for joining and us on this occasion. Today we are going to have a very interesting talk and informative session. I hope we all will enjoy and get benefited out of this lecture series. I welcome you all once again to this session. Thank you. Jai Hind. Namaskar.
Namaskar, sir. Thank you,
Over
sir.
to ma'am.
Thank you, sir.
Dr.
Thank you, sir.
Sapna.
So, before we proceed further, I would like to invite our chief guest of today's program, Professor P.K. Aluwalia. Sir, we would like to hear something from you also before we start our program.
Thank you very much. It's a matter of great joy for me, especially that we are once again starting this series. And I'm glad that today's session is being chaired by Professor Anvesh Mazumdar, who is Dean Academics at Homi Bhabha Center for Science Education, TIFR. In fact, I would like to express my gratitude to HPCSC for helping us in organizing some initiatives in physics education research. And one initiative which I would like to mention particularly is that for the last 2 years, we have been publishing in IAPT Bulletin a regular column written by Dr. K.K. Mashood on the various dimensions of physics education research. Not only that, Homi Bhabha Center for Science Education, under the guidance of the director, Professor Arnav, we have been also able to together bring out a very good publication out of those articles which have been published in IEPT Bulletin. And I will like to record a thanks for that also. This time when we were planning this series of lectures, we thought that we should really give this platform to young researchers in physics education research. That's very important because I believe that PER should be one of the research areas in the physics departments in the country. And lately, under national education policy, we are seeing that 4-year degree programs have been started in education in different IITs and in the country also. And I think that is what is a very big opportunity for subject education researchers to come forward on the university campuses and work vigorously in this particular area. And I think PER is a kind of a leader in subject-based education research because of very good work, which we can see in physical review, PER. We can see that in physics education, IOP. And I would like to tell the members present here that we also have in India a journal which is the responsibility of IAPT on physics education itself. And I would like that more and more people from outside and within the country should come and publish there. It's always a great privilege to have Professor Ghatak. And let me also mention this here, that Professor Ghatak is one of the quantum hundreds who were really honored for that kind of a international recognition. And if you will go to the IYQ page 2025, you will see his photograph at the first place. So congratulations, sir, for that. And your blessings are always sought by us.
Thank you. Thank you so
We are
much.
starting this series with Jaya. I met her in ICP 2025, and I was very glad to know what she is doing. And she is from India, and she has done very good work. Lately, I saw her work also, which has been published. And I believe that today's lecture is also going to be very insightful, something which can be practiced in our classrooms also, and get some useful research done about uh, learning in the Indian context itself. That's very important, that we should learn all these things in the Indian context.
Maybe at a convenient time she can write up something for IAPT. That would be lovely.
Yes, sir. We will definitely encourage her, sir. She is welcome to write for our physics education, our IAPT bulletin.
Yes.
And I think she has joined IAPT as a life member. So we will have the benefit of her presence as a young researcher among us.
Wonderful.
So thank you very much, Jaya. Thank you for accepting our request, and looking forward to listening to your research. Thank you all. Over to Sapna.
Thank you, sir. Thank you, sir, for your motivating words. Now, as we move ahead with today's program, I would like to hand over the proceedings to Professor Anvesh Mazumdar, who will chair today's program. Before doing so, it's my privilege and great honor to present a brief introduction of our esteemed chairperson. Professor Anvesh Mazumdar is the Dean of Homi Bhabha Center for Science Education, um, a premier institution under the Tata Institute of Fundamental Research, Mumbai, and currently serves as the national coordinator of the Science Olympiad program in India. He is widely respected for his contributions to physics education research, astronomy education, and the development of innovative approaches to teaching and learning physics. His work focuses on conceptual understanding, problem solving in physics, undergraduate research, and nurturing scientific thinking among students and teachers alike. Apart from his remarkable contributions to science education, Professor Mazumdar is also an accomplished researcher in astrophysics with several internationally recognized research publications to his credit. Through his leadership in Olympiads, teacher enrichment programs, and PER initiatives, deep commitment to improving physics education, he has inspired countless educators and the young learners across the country. On behalf of all the participants and IAPT RC23, I extend a very warm welcome to Professor Anvesh Mazumdar and thank him for graciously agreeing to chair today's session. So thank you, sir, and over to you.
Thank you, Professor Sharma, and it's my pleasure to be here today. And thank you for the very generous introduction. But it's indeed a great pleasure to see that IAPT has again, IAPT, this particular RC has again restarted this lecture series on physics education research, which I think is much needed, as Professor Aluwalia mentioned, that this is something that IAPT as an organization is the right body to push forward, and which it has already been doing through the IAPT bulletin with the very nice articles. And this is one more initiative, so I deeply appreciate IAPT's initiative in this. And thank you for inviting me. This is an honor for me to be here today, especially among such distinguished people here. So let me introduce today's speaker, Ms. Jaya Kashyap. So Jaya did her BSc honors in physics from SGTB Khalsa College, Delhi, followed by her MSc in physics from IIT Roorkee. And after a brief stint of teaching at the Middle and Intermediate International School in Bengaluru, she joined a PhD program in physics education research with Professor Chandralekha Singh, a very well-known name in this field, at the Department of Physics and Astronomy at University of Pittsburgh. And she is expecting to graduate this summer, as we hear. So Jaya's work has spanned several areas in physics education research, including advanced student sense making in upper level electrostatics. I believe some of that we will hear about today. Development and validation of guided inquiry-based tutorials, misinformation in quantum information science and technology, and the relationship between course grades and physics identity and recognition for introductory physics students. So this is indeed, I mean, a very wide range of fields that she has been working on. She has also already published several papers in peer-reviewed journals and also presented in prestigious conferences. So clearly, she's an upcoming name in physics education research, I'm sure. In the coming years, we'll hear a lot more about her. And it's my actually my special privilege to chair this session because, as it happens, that I have never met. Well, I met Jaya in person for the first time in ICP last year, but we had met online in the Vigyan Vidushi 2020 program. That was the inaugural edition of the Vigyan Vidushi program, and Jaya was a student in that. And actually, because it was the first year of the program, so we were not sure about whether we should introduce physics education research, whether we should have some lectures, but we thought that why not? It may be interesting for MSc students to learn about such a field, and not many may be aware of this. So we had, I think, I don't recall exactly, maybe only 2 or 3 or 4 lectures in that edition. And I'm very happy to see that it really encouraged her to to take up physics education research as a career. And so it's a here at TIFR and HBCC, we are very happy that she's our VV alumnus who has gone on to do very good things. So welcome, Jaya, and without further ado, I invite you to start your talk. And I request our audience members to kindly mute your microphones so that I mean the talk is not disturbed, because sometimes there is an echo. So if you can kindly do that before we start the talk. Yes, Jaya, over to you. You may share your screen and start.
Thank you so much for inviting me for this talk. I'm extremely grateful, and thank you for providing this platform. And I'm so happy to see everyone here, some people whom I met at the conference, and some people whom I'm so delighted to see them here. So I hope my screen is visible.
Yes, it is visible.
Yes, it is. Yes, it is visible.
Okay. So today I'm going to talk about student sense making during different solving physics problems. And this work is done in collaboration with Dr. Chandralekha Singh. So I will just start with the background that electricity and magnetism is considered as a challenging course for students. All the instructors who have been teaching electricity and magnetism, they are familiar with the kind of struggles that students usually have while learning different concepts. So this subject requires students to have good mathematical knowledge as well as physics knowledge. And apart from that, it also requires students to have the ability to integrate mathematical knowledge and physics knowledge together. And most of the times, students usually are equipped well with all the concepts. They know calculus, they know vector, they know all those mathematical skills, and then they learn about physics concepts, but they have difficulty in integrating those concepts together. So this is something which students really struggle with. And for us, it is important to understand, we as researchers or instructors or educators, we want to provide support to students. We want students to develop expertise in learning physics as well as in solving different physics problems. So it is also important for us to understand what are the things that students actually struggle with. It is important for us to see what kind of thought process students usually have when they're solving problems, what kind of knowledge resources they activate, or what kind of knowledge resources are required to be activated to become an expert problem solver, or to become an expert in physics. So in order to do that, we need to understand their thought process, their thinking process, And therefore, we talk about sense making. We want to see how students actually do sense making when they are solving problems. So, what is sense making? It is a process of figuring out how to solve a problem. So, even in our day to day life, we usually do sense making, like when we are going for a trip and we do not have GPS and we want to figure out where to go. We do try to make connections about different things that we have in our mind, and then we try to figure out a way to solve or deal with that particular situation. So, in the same way, in the context of physics, when students are given a novel problem, so if they are given a problem that they are already familiar with, that can become an exercise for them. But if they are given a problem that they have not seen before, and then they are given a specific amount of time when they try to navigate through the problem, it can involve sense making. And why is sense making important? Because it helps in creating connections between, so students can have different concepts, different knowledge, but it helps in creating connection. It helps in integrating intuitive and formal knowledge. And it also leads to generation of new knowledge. So maybe students are not familiar with certain things, like they have learned about different concepts, but they do not know certain things. So when they spend time in doing the sense making, they are able to generate some knowledge for themselves. So it is important to support the sense making process, because if they are able to figure things, if they are able to learn to figure things out, even if they are like not doing things correctly, but they are trying to figure things out, that can eventually lead to the generation of new knowledge, that can eventually lead to be able to learn new things or generate new things. So here what we did was we looked, so as as a part of development and validation of a tutorial on method of images, what we did was we also looked at sense making of students, and we like through different interviews, and we mapped that sense making process to epistemic game framework. So what we did here was, students were given different problem sets. They were given a pre-test, tutorial, and post-test, and students were asked to solve those problems on Zoom in real time, and they were asked to talk out loud. So whatever they were solving, whatever problems they were doing, we asked them to talk out loud so that we can see what in real time what kind of problem solving or sense making they are doing. And we recorded and then analyzed the data, and then we mapped it onto epistemic game framework, which is proposed by Tuminaro and Redish. So according to this framework, we can say that solving a problem is like playing a game. So for example, when we play any particular game, there are certain rules and strategies. There are certain rules to start the game, like it has some kind of entry condition, and then there is some kind of exit condition that eventually this is the goal of the game, and then there are different moves. So in the same way, when students solve different problems, it also involves entry conditions. So if they are given a problem where they have to draw a diagram, or if they have to find an electric potential, so they have an entry condition, and then eventually if they have to find, if they have to draw the diagram or get any kind of numerical expression or mathematical expression or numerical value, then that thing can be the exit condition. And they start from entry to exit condition. They navigate through that whole process of problem solving, which involves multiple moves. So Tuminaro and Redish also identified 6 different types of games. And in our research, we tried mapping the sense making of students that we observed on these 6 games here. So I'm just going to show a glimpse of how like these games look like. So for example, there is pictorial analysis game. So there can be some concept that they try to identify, and then they use some kind of external representation. So maybe students can choose to draw a diagram, or they can choose to have a free body diagram or a graphical representation. So they have to choose some kind of external representation, and then they try to tell a conceptual story and then fill in the slots, or eventually label a diagram, find the potential, find where the charge should be present, all those things. In the same way, there are other games like mapping meaning to mathematics, where they have a physical situation and then they try to translate it using some mathematical entities, and then they like manipulate different symbols, and then they evaluate whole story. Or then there can be transliteration to mathematics. Maybe they already know some kind of problem, and then they try to use the same concept to map it onto the problem that they are solving now. So based on these structures of the game, we mapped the sense making of students onto these games. So here I will be showing some examples of like how students did sense making. I will not be going in much detail, but I will just like show what they did overall. So for this part, I will be talking about a particular topic, which is method of images for advanced electricity and magnetism course. And again, this study was conducted in a large research university in US. So the advanced course is what like students learn after they are done with the introductory electricity and magnetism course. So this method of images is what students learn at that level, and it is one of the techniques that can be used to solve certain kinds of boundary value problems when certain situations are satisfied. And so like for example, if there is a charge and there is a grounded conductor, that can be replaced by an image charge, and then in the shaded region, in the region of interest, this same electric potential, like the expression for electric potential, can be obtained by replacing the conductor with the image charge. So for this similar kind of problem, students were given this scenario where they have a grounded conductor and there are two charges present, and they were asked to write the expression for electric potential. So this problem can be solved using method of images. And for that particular, if that method is used to find the electric potential in this shaded region, they can have two image charges, and then the expression for electric potential can be written down for the shaded region, the region of interest. Now, I will be showing some examples of how students did in this kind of problem. So, for example, there was one student G1. So for this particular case, we can see that this student drew the diagram. So when they were given this expression, this problem statement, they were not provided with this particular diagram. They were just given this problem statement. And what we found was students started by drawing a diagram first. So it shows that they realized that they need to have some kind of representation to find the expression for electric potential, to understand where charges should be present. And it shows that they entered into pictorial analysis game. So they read the problem statement, and then they placed charges at different positions, and then they tried finding out where the what should be the expression for potential. So what kind of sense making patterns did we see here was, so they kind of misinterpreted the question, and they placed this negative 2q charge on the negative z-axis. So there was some kind of misinterpretation of the problem statement, but then they tried thinking that, okay, let me think how other charges should be placed so that I can find what the potential is. So in a way, when they were thinking about those things, we found that along with the diagram, they were also trying to use some mathematical expressions based on whatever physical situation they had. So they were into mapping meaning to mathematics game. So here we also saw that there was some kind of nesting of epistemic games. So nesting means they were playing one game, and within one game they entered into another game. So it shows that students, when they are doing sense making, they can be in different modes, they can be playing different games, and those games can be intertwined as well. So here, this student was little confused with how this problem can be solved. And then for some reason, they thought that maybe a Laplace equation is something that can be used to solve this problem and find the expression for potential. So it also showed they were kind of like confused, and they were mixing like different techniques, or like they did not realize that if there is charge, Laplace equation is not something that they should be using here. And then they also thought that instead of charge density, they thought that if they somehow figure out some kind of charges such that it adds up to zero, uh, this will give them, for the Poisson's equation, they can get the Laplace equation by just balancing these charges, like having 2q minus 2q add and it becomes zero. So they were having some kind of confusion about what is local charge and what is the net charge density. And also, it's like when they are solving the problem, they can be having they can be having a different, they might be using different resources which might not be consistent with the actual physics, but we still appreciate their sense making because they are also trying to figure things out at this point. So there is always some kind of local coherence that is observed when students are doing sense making. So maybe globally this could be inconsistent with the physics concept, but they are also trying to do some kind of local coherence here. But we observed that there was some kind of confusion. And at that point, they just said that, oh, if you solve the Laplace equation, you should be able to get the expression for potential, but they just stopped there. So at that point, when interviewer just did a small nudging by asking, are you sure you are done, or you want to think about how the expression of potential can be returned? So we saw that student actually, like the thought process of student changed, and then they realized that, oh wait, maybe I don't have to solve this whole potential, but maybe based on whatever charges I am able to see here, I can just write down the expression of potential using superposition principle. So we also saw that small nudging, or if a small prompt is given, that can change the thought process of students. And we did see that student did not check boundary conditions at this point, and when they were asked to write the potential, they were little confused with what should be the distance here. So there was some kind of confusion in writing the distance, and they were still carrying this idea of balancing charges. Like they just thought that they have to somehow balance charges in this particular situation, and that idea of balancing persisted with them. So this is example of one of the students who solved this problem. Now I'm going to show another example. So they were given different tests, like pre-test, post-tests, and these tests were in different forms, like unscaffolded or scaffolded. So the previous problem was unscaffolded, where they were given the problem statement, but this problem is in the scaffolded form. So scaffolded means it is broken down for them. So they are given this scenario, but then they are also asked that, okay, you should sketch the situation, and then you should try to write number of image charges. And once you have image charges, again, sketch the situation, check boundary conditions, and find the expression for potential. So again, if they use method of images, they should have like 3 image charges for this particular scenario, and then they can write the expression for potential in this shaded region. So now what we saw for the sense making of G1. So again, this student G1 started by drawing a diagram, which again shows that after reading the question, even when the diagram was not provided to student, they started by drawing something. Again, they entered into pictorial analysis game. And then they started thinking, how many charges do I need to have? And then they started with 2 charges, and then they thought maybe this will satisfy the situation. But then when they were asked in the scaffolding, like when the question said that you should check boundary conditions, that made them realize that maybe these 2 charges are not enough. Maybe this is not satisfying the boundary condition. And then they evolved further. They added another charge here, and then they drew another diagram when they were asked to draw another picture where they have to show all the image charges. This is the third diagram that they drew. And then they went back to their first diagram and placed this charge here. So what we have seen in this whole process again is that they were drawing multiple diagrams. So they started with some initial assumption of how many image charges they should have. So they thought that, okay, maybe there are 2 planes, so maybe I should have 2 image charges here. And then they used the superposition of different planes, and then This time, the same student actually checked the boundary condition because they were prompted to do that. So we are seeing how their sense making is evolving, because the same student in case 1, they were not prompted at that point, but now we see that how they are evolving and they did check boundary conditions. And then they were a little confused with if this is like semi-infinite or finite planes. But then we saw some refinement in the model. So they drew multiple diagrams and then they evolved their sense making, which is again a good thing. For the same problem, there was another student, G2. Again, that student started by drawing a diagram. They entered into pictorial analysis game, and then they started thinking about how many image charges are required. And then when they were asked to check boundary conditions, they thought that maybe they can just have 2 image charges with the magnitude of charge can be chosen as half and half, such that at the origin, the boundary condition is satisfied. So what we saw here was, again, they had initial assumption that there should be 2 image charges because there are 2 conductors. And then instead of 3, they just thought that if they have 2 image charges, Q over 2, Q over 2, that should be able to satisfy boundary condition. And they did check boundary condition. So it means they were actually trying to work through the problem. They were following what the question was asking, and they did check boundary condition, but they just checked at the origin and they felt that, okay, it looks good. And then they just said that this is how it should be, and based on that they wrote down the expression for potential. So again, we saw that they persisted with this idea that the magnitude of the charge can be Q over 2 for this problem. And then it also, when they solved other problems, they carried along the same idea to other problems as well. For the same situation, then there is another student, G3, who solved the problem. So again, we can see that G3 started by drawing a diagram, and then they started thinking how there should be different regions, and then they eventually figured out there should be like 3 image charges, but then they were confused with what should be the sign, and they kind of like, instead of grounding, they were a little confused with how the charge should be distributed. And then again, this idea persisted. So they continued with the idea of charge separation here. So again, we have seen that this student was trying to think about, if I have 2 planes, maybe I need 2 image charges, or then they slowly evolved to the idea of, okay, they need 3 charges now. So although they figured out that there should be 3 charges, but again, there was some inconsistency in the reasoning. So sometimes when we see that students are solving problems correctly, and if we do not know what is going on behind, like what thought process they are having, it is possible that they can come to the right solution, but with some inconsistent ideas or inconsistent reasonings. Then there is another scenario where students were given the scenario where there are again 2 grounded conducting planes, but now these 2 planes are placed at 60 degrees. So now there is a charge, and for that they had to write the expression for potential. And again, if method of images is used for this scenario, there can be 5 image charges. So for this problem, it was at first given in the unscaffolded form. So in the unscaffolded form, they were just given this problem statement, but there was no scaffolding provided. Later on, they were given the same problem in the scaffolded form, and there were multiple questions. And one of the questions was, they were asked how many image charges are required to solve this problem. And then they were also given some options here, like 3, 4, 5, 6. So again, for this problem, there can be 5 image charges, which can be used to find the expression for potential in the shaded region. And now we will see how students approached to this problem. So this is again student G1, when they were given unscaffolded version, when they were not given options. They started with the given figure, they started labeling it. Again, no diagram was given to students at this. They were provided with this diagram where they started labeling, but all other diagrams are drawn by students, even when they were not asked to draw. So here we can see on the right side, there are two figures, and the student started by thinking about what should be the geometry, how they should be placing all these charges such that there is symmetry. And then they figured out that there should be 3 image charges for this problem. So again, this problem requires 5 image charges, but they went with the idea of 3 image charges. But at the end, they saw that the boundary conditions were not being satisfied, but they just ended their thought process at that point that there should be 3 charges. When they were given the scaffolded version and when there were options given, we saw that they were actually able to recognize that, oh, maybe I was thinking about 3 image charges, but maybe I should think about 5, because they were not thinking about those number of charges. And then they also realized that there can be a symmetry in this situation, and then they can have 5 image charges. So again, their thought process evolved. So this included a long thought process here, but I'm just showing the final diagram here, which this student obtained at the end. And they were also carrying some idea of balancing forces. So instead of seeing that they have to see that boundary conditions are being satisfied, they were carrying some idea of balancing forces at this charge, which was not completely consistent with the physics. But still we saw that the idea of balancing, the same student who was thinking about balancing charges at one point was now thinking about balancing forces. So somewhere they're also carrying ideas. Sometimes those ideas can be correct, or there can be inconsistencies sometimes. So this was student G1. And then again, we saw that their sense making involved geometric exploration, and sense making about boundary conditions. So they were looking at boundary conditions, and again, we see there is some kind of local coherence here. And there is the idea of balancing is consistent. So they are just carrying that idea. At one point, they also thought that maybe there should be Q over 2 charges, but then they did not go with that idea further. But we do see that there is evolution of their sense making. It has been changed, it has been improved, and they eventually figured out how this problem should be solved. So which is again a good thing. For the same situation, if we talk about another student G2, when they were given unscaffolded version of the problem, this is the student who was saying that there should be Q over 2 charges for 2 planes. So again, this student started with the same idea that when I solved the previous problem, there was Q over 2, negative Q over 2 charge. So again, they carried along that idea that maybe this problem can also be solved in the same way. And again, there are 2 planes, so maybe I should just use the same idea. Although they later on realized that it is not satisfying the boundary condition. They tried adding one more charge here, but it did not help much. And then they further tried thinking about it by drawing more diagrams. And then somehow they figured out there should be more charges here. So again, this was not like they were not able to get the final expression, but still there was some improvement in their thought process. They were able to find that, okay, there should be more charges, there should be something more so that they're able to satisfy boundary conditions. And again, when they were given the scaffolded version, and when they read all those options, 4, 5, 3, 4, 5, 6 image charges, that kind of helped them in realizing that there can be more image charges. They were just thinking about 3, but maybe there is a possibility of 5. And then they also realized that there is a symmetry in this situation. So again, there is like a good, we are seeing like how this student is evolving. Although at the end, the placement of the charges was little inconsistent, but still there is a huge improvement in how they started. And then slowly they started recognizing that how these charges should be placed. And again, they were not able to find that the boundary condition is being satisfied with this configuration because of a little inconsistency in the placement of charges, but still they were doing better, and it should be appreciated. So again, we have seen here that they are reusing the idea of Q over 2. So we are seeing there is local coherence here, consistency across different problems. They are carrying along that particular idea. They're playing different games, as I mentioned, like they're drawing pictorial, the diagram, they are playing pictorial analysis game. And within that game, they're also trying to figure out how what they have already learned. They're using the idea of Q over 2. So they're doing the transliteration to mathematics, and then they're trying to figure out what should be the expression for potential. So these are all examples of how students did sense making. Then there is another student, G3, who was thinking about charge separation earlier, and then we found that they kind of carried along the same idea. This student did not spend much time in the unscaffolded version. So only when they were given the scaffolded version for that problem, this was the figure that was already given. But we see that they drew 3 more figures even when they were not asked to draw. So we are seeing that they are trying to do sense making. They're trying to think through the problem and drawing more diagrams here. They're trying to relate it with other problems that they have already solved. And again, this student was able to find that there should be 6 image charges. So again, if we give them some kind of MCQ problem and we see that they are saying that there should be 6 image charges, we do give them full points for doing it correctly. But there is some inconsistency in the idea here itself. Like they're able to recognize the symmetry, but still there is some inconsistency, which we are able to see when we are looking at their actual sense making and thought process when they are solving in real time. So the idea of chart separation stays here, and then they were again thinking about the logic, as they were saying if there are 2 planes, there should be 2 charges, and then they were still thinking about that. They were also trying to think about the same logic here. Instead of actually checking boundary conditions after placing charges, they were trying to go with the same logic. And although they found the correct number of image charges, there was some inconsistency in the reasoning. So based on all these examples, what we have seen is for all these cases, there is a use of diagrammatic representation and which is like consistent everywhere. So all the students were drawing diagrams. At certain points, they were given space to draw the diagram. They were asked to draw the diagram, but we also observed that they were drawing more number of diagrams than they were asked for. Because they were also doing the sense making in real time, and they were trying to think through the process. So this pictorial analysis game is prominent all over the problem solving here. We also observe nesting of epistemic games. It means once they draw the picture, they play different games and they try to do different things, and even like whatever concepts they have learned based on that, or like they try to map a mathematical knowledge to some kind of analysis, or they use the analysis or the physical situation to map it to mathematical expression. We also observe that there is sometimes mixing of concepts. So like students can sometimes get confused about what is total charge, what is charge density. And this can be very common even when they are doing like what is speed, what is velocity, or there can be different kinds of confusions that students can have. We also observe that if a small nudging is done, so for example, if there is some kind of scaffolding or nudging done, that can actually change the thought process, that can actually like change the way students are thinking. And if we are able to figure out where these nudgings are helpful, that can actually improve the problem solving process of students, and that can help in to help them to become more experts in problem solving. So, and the struggle with the distance interpretation of the potential was very common. this is something which we even saw across students. So when they were asked to write the expression for potential, they were always confused about whether they should measure it from origin to the point charge, where to the charge, like that should be the distance, because they already spent a lot of time in figuring out where should the image charge be placed. And when they write the expression for potential, they just use the same distance instead of realizing that they have to find potential in the region somewhere, and they should be choosing some particular point and then write the distance from the point charge to the point. So this was something we found that students were struggling with potential, and this thing can also happen when they are dealing with like forces, electric fields, or different concepts. Again, the idea of balancing state. So we see that sometimes when students have certain ideas, and if they are not corrected at the right time, some kind of ideas can just persist, and it is possible that those ideas are inconsistent with the actual physics, and that can sometimes hurt them. Again, like we saw that there was iterative refinement of figures. So all the students were trying to kind of draw more figures to make it much better. So again, if like students are provided that space and they're given some kind of incentives or appreciation that drawing a figure is important, not just getting the final answer, but the process itself is important. And if they are given more incentives for spending more time on the process, that can actually improve their problem solving. And then again, we saw that there was local coherence. So when we see that students are doing the sense making, there are certain situations when they can do plug and chug. It means they can just use the formula and put the values. But there are certain situations where they are actually trying to think through the problem, and for them locally it looks consistent. There is always a local coherence, and they feel like, okay, based on this situation it looks correct to me. And there is a possibility that there can be lack of global coherence. Overall there can be many inconsistencies, but when they are doing sense making, there can be evidences of local coherence. And then again, the ideas can persist. And it is important to see that sometimes like students, again, like when they were guessing problems, there was local coherence here. And scaffolding can help students much more, like when they are solving different kinds of problems, and it can help in developing expert like evolution. So we can see that initially they are not expert, but they can slowly develop expertise by refinement. So these were certain things where we saw that students did sense making. So we saw that how for the same problem, different students had different approach, like they have different types of sense makings, but still certain things were very common across students as well as across problems. There were certain kind of consistencies. So what we have seen here is so this study involves in-depth comparison. So we have seen like students solving same problem, multiple students solving same problem, as well as how single student is evolving over different problems. And then we have seen that there is persistence of a certain kind of knowledge resources across different problems. So they just carry along the same idea, and then they just use same resources across different problems. Sometimes that can help, sometimes that can hurt. And then problem solving involve like multiple drawing diagrams, as we discussed. So successive attempts can actually improve the problem solving. And then we have seen that if small nudges are provided to students, small scaffolding, that can actually lead to significant improvements, and students can evolve from incorrect approaches to correct approaches. So again, it's important for us to see where they need the scaffolding or the nudge. And then we also saw that students were drawing like 3D diagrams at first, like they were drawing all the planes, but like they also evolved in how they were drawing the diagram. It also changed like what kind of symmetry they were using, whatever viewing angle they are using. So it's again something very important, like how diagrams themselves can evolve and they can try to find what is the best way of drawing a particular situation. And then we saw that for this kind of scenario, there was struggle in finding image charges, what should be the magnitude, to see how many image charges are required. But again, we have seen that they were still trying to think through the problem, and there was some kind of consistency in this whole situation. So based on this, as we as instructors, educators, researchers, what are the things that we see important here? We see that providing scaffolding, such as prompts on symmetry, all these things can actually help. So again, like at first we need to understand where scaffolding is needed, and then we can provide them good scaffolding, good support, so that they do not stay with the wrong idea for a longer time. We can also like draw different, we can provide them complex problems with increasing complexity, but we can also provide like scaffolding. So as we have seen, when we break the problem down into small parts, they actually are able to think through the problem. So instead of just reading the statement and trying to find it, sometimes like providing in the initial phases of learning, providing them some kind of scaffolding can actually help them. And once they start developing expertise, those support or scaffolding can be removed so that they can learn to solve problems by their own without much support. Also, like teaching different kinds of visualization strategies. This can be important and helpful. So, like, it's not just the diagram, but what kind of diagram can be drawn, which can be very efficient or effective for a particular kind of scenario can be helpful, and they can be given like feedback for different types of diagram qualities, of different kinds of reasonings that they are using, not just like the final answer that they are trying to find. And again, there can be explicit like comparison before solving, so that they can see like what are the important things, like how there are differences, how certain things are same or different, like what is the method that cannot be applied in a particular scenario, and they can just not use certain things which are inconsistent or not applicable in a particular scenario. And then we can also encourage them for the reflection. For example, if they are solving problems, we can also ask like them to spend more time on, does it look consistent? Is it, for example, when we ask them to check boundary conditions, they realize that the placement of image charges, the number of image charges was inconsistent. So providing certain checkpoints, certain reflection points can also help them so that they understand what is the right way of solving the problem. And then again, connecting geometric symmetry to number of image charges and boundary conditions, as we discussed, like is something that is important, like we can encourage students. And also we can provide them some time to explore. So it's not just that they have to get the right answer, but providing them some kind of space where they just focus on more of spending time, more of doing sense making. And again, think aloud discussions are very helpful, because when we were observing sense making of students, they were more like because they were being think aloud, they were also like thinking through the process. Same student, if they were given a paper test, they would have done differently than when they were asked to talk out loud, to when they were asked to think through the process. And then peer collaboration, like research has shown that peer collaboration also helps. So when students work in group, when they work together and do sense making, that can also help in co-construction of the knowledge. So that itself is like a very important thing. And again, like instructors, when they know what are the places where they need nudging, like when we provide that kind of support, that itself can be very helpful. And again, like for us, it is important to at first figure out what are the places where they need nudging, and then we can help them developing expertise. So yeah, these were like important findings and implications from my research. And thank you so much.
Thank you, Jaya, for a wonderful talk. So I think we can take some questions now. And maybe it would be good if members can just unmute and ask the question directly. Yes.
I'm Jaya Kashyap.
Oh,
I
okay.
have a, I mean, it was a great learning experience for me. I know I have taught various things in physics at MSc and BSc level, but I never think of such things. So this is a at what level should you do such exercises, analyze the question papers and answers and things like that? It's a I mean, we have never done that, and neither our teachers ever analyzed our answers and things like that. So it was a learning experience for me. I thought, Dr. Majumdar, I thought I should tell you that as a teacher in IIT, and that how do you analyze the answers? This is a thing, that's a whole new thing that has come up. So we never how to incorporate that in our is it necessary to do that at the school level or just at the school level or at the college level or at the university level or at all levels? I don't know. So I just thought, thank you for organizing that. This
Yeah, thank you for your comment. Yes. Yes, indeed. I mean, I think it's a common experience for most teachers when they become aware of physics education research. It was certainly for me, and I have seen the similar thing in other teachers also, that we just think that, okay, we are doing our job, we are going there and teaching, and somehow this will be transmitted. And we never really reflect and think as to exactly what is going on. But I think it also matters to the, I mean, as to what audience we are teaching. I think IIT classroom is very different from a normal college classroom, where some students may have, I mean, so the kind of difficulties that students face, the kind of backgrounds that come from, the prior experience that they have in tackling difficult problems, I think that also changes the way they think and etc. So it's, I think, yeah, it has been a learning experience for me also, I must admit, to learn to think about these things. Yes. So thank you for your comment. Yes. Yes, Mashood, you have your hand raised. Yes. Others, if you want to ask a question, please raise your hand and we can go in order.
Thanks, Jaya, for a nice talk. My question is building on some of the instructional implications that you have suggested. So you have said that teachers should, identify where appropriate nudges should be given, how it should be given, and all. But can you elaborate on that from a teacher training program? Suppose we are conducting a teacher training program and we have a group of teachers. How can we actually train them operationally, like design some modules for teacher training for the purpose of orienting themselves towards sense making? How can we develop some modules? How can we train teachers? A little more operational details on that based on your studies, can you provide?
Yeah, thank you so much for the question. So I think like what we have seen here, one of the important things that we have seen here is like how scaffolding, like breaking a problem into sub parts helps. So maybe like we can, I mean, this whole thing does require a lot of database at first, because as Dr. Mazumdar said that based on different population there can be differences, and therefore we cannot generalize, but still for instructors, for teachers, we can at least try to like train them that a problem can be broken down. So for example, if they are giving some kind of test to students, instead of just focusing on the answer, when they are teaching students, they can try to give them more incentives, more points for certain steps, like because most of the time students are just given like points for correctness. So like they should be given more points for how much problem solving you are doing. And also like as we have seen a lot in the research, that working in group helps a lot. And I have seen like this thing that most of the times when people work in group, it really helps in co-construction. So even teachers can incorporate those techniques in the class when they are teaching students, that you can give certain kinds of problems and then ask students to work in group, and then just solve, and again like start with the scaffolding broken down part, and then they can slowly develop the expertise, and then they can be given different kinds of problems which does not involve a lot of support. So maybe we can start with that, and then if we have more data on what are the struggles, because certain things are very common, like when I'm talking about a kind of difficulty, there is a possibility that an instructor who teaches the course might observe a similar kind of difficulty, and then they can work on that part. But there can be differences again based on what kind of population is there. So in general, at least like for teacher training, we can start with collaborative learning with the scaffolding. So those things can be helpful.
Just a follow up, Anvesh. So is there are two ways, like one can give the, like it can be part of the assessment, like you give some homework or something and then they submit the answers, and feedback can be given to that. But I was getting the impression from your talk that this is much more going to be much more productive if an on, like in the moment feedbacks are given, and if it is done in the classroom, like rather than okay you give homework then they submit it, rather than it's an interactive mode would be much more productive if real sense making has to unfold. Is that a correct
Yeah, I think like I do agree with like what you are saying is like in the classroom, like sometimes we as instructors mostly focus on giving lectures, but I think the thing that should be focused more is active learning, like students doing more stuff. So once they are taught a particular topic, maybe in the classroom we can ask them to solve problems, like sit in the group and do more of problem solving in the classroom, like if they or even like learning the concept through problem solving and collaboration. So we can incorporate more active learning where students are doing more stuff than instructor, and instructor is just like walking around and just helping or working as a facilitator. So if students are working in group and if they are struggling, instructor can just walk around in the class and just go to different groups and see okay what is the struggle, and for that particular thing they can provide scaffolding. That can also be a helpful thing, like with more active learning practices in the classroom.
Okay, thank you.
Thank you.
Thank you.
Yes, Professor Ahluwalia. Yes.
Yeah, thank you, Jaya. I enjoyed your lecture, and I think there was a lot of learning from it, particularly the game framework which you talked about. We were not knowing about it. I mean, this is something really wonderful. There was one thing which I wanted to ask. You carried out all these in a Zoom session. Am I right? And there was a lot of loud thinking in that, and then students were coming and participating. How many people were there in the Zoom session itself who were participating in this part? And how you could control them, in doing these kinds of tasks. I mean, you put them into small rooms and then, try to put somebody else also to look at those rooms and come out with what they are doing. How you carried out in the Zoom session itself?
Yeah, thank you for the wonderful question. I think like I did not mention detail. So this study was part of the development and validation of the tutorials, as I mentioned. So in order to collect the qualitative data, like when we were working on the development of the tutorials and tests, we were conducting individual interviews with students. So this study does have limitation that we had very small number of students. Like I conducted interviews with like 13 students in total, but I did spend like 6 hours with each student for two of the topics. So I was doing like one-to-one interview sessions, like just one student solving problem in front of me, and this whole thing is being recorded. So that is how we collected data. So like as I said, method of images, and then another project that I worked on is related to Laplace equation. So each of the topics I spent like 3 hours with each student doing pre-test, post-test, and tutorial. So it was mainly like one-to-one session, and it was more like students were they volunteered for this session. So we just released out an advertisement that we are going to give them some like monetary award. We will just give you some money for coming and doing this interview. And then some of the students agreed, and overall we did like interview with 13 advanced students in total.
Okay. So making a transition from this kind of a one-to-one interaction in a classroom where other students are also sitting, what are the challenges which you feel will be there in the classroom itself? Because, loud thinking which you are doing for peer learning, that is very crucial. There is not just one person who is talking. There are a lot of students who are listening, and they may even raise questions on what is happening. They may suggest something. One scaffolding you are offering, but another scaffolding can come from the group who is actually listening to those kind of loud thinking processes. What's your take on that?
Yeah, I think like kind of interviews that I did one-to-one, it is not possible to do with each student in the classroom. Like if we have 30, 40 students, or even sometimes there are like 200 students in a class for introductory courses. So it is not possible to do complete one-to-one like interviews and looking at sense making. But then depending upon the size of the class, if like we are providing the scaffolding, and then when they are working in the group, we can at least encourage them to discuss with each other. That will involve the talking out loud process, and then the type of structure that we are providing. So like there are various research based tutorials and problem sets that are available. So if we use those content in the classroom, so we already know that there are evidences that it worked in a certain situation, so we can go with those kinds of scaffolded tests which are available, and then we can ask students to work in group and talk out loud, and then based on that we can analyze the process. And then it does require like a lot of database, like a lot of research is needed to observe how students do. So again, it is like a place where we have a lot of scope to do research and find like the thought process of students in different areas, in different kinds of scenarios, different types of student background and universities. So yeah.
Thank you, Jia. Thank you very much. Enjoyed it. Great.
Yeah. Let us suppose you came back to India and started teaching in one of the Delhi University colleges, and you are asked to teach electrodynamics, so which is part of the course, and you have a class of 40, 50. What would your advice be to a teacher? Teaching
Okay.
BSc students you said that you did your BSc from Delhi University, right? So
Yes.
if you become a teacher, what would you do? And have I made my question clear?
Yes. Um, I think it's a great question, and I'm also going to start teaching at Pitt in my university from tomorrow. So I'm going to have like my first class, and I'm thinking through all those things again. So maybe for the first time, what advice
What is the student strength? What is the student strength?
I have 40 students. I am teaching mechanics, like introductory first year student course. Those who are from medical, like biosciences, all those backgrounds. So I'm going to start with that. So like first thing is I have to just start with the teaching thing. Like I'm excited for that. And then the second thing, as you were asking, like what are the things I can incorporate? So I'm again thinking about at least starting with the peer collaboration. So I was planning about different problems that I can give in the classroom where students will be talking to each other and doing like peer collaboration. And then like even for homeworks, they can work together. I was also thinking about making them more excited for the physics by like having more, like just click the picture of physics that you see around, giving them more demo sessions, all those things. So again, for electricity and magnetism, if I get a chance to teach, I will start with the same thing. Like I will also use like research based sorry, I think you are muted, I did not hear.
Oh, sorry. I thought that after you finish your mechanics course, maybe we should have an interaction that how you could incorporate these concepts in your actual teaching. So this is
Yes.
mechanics to undergraduate students. These are in coming to your university. So they are about 18-year-old or something like that.
Yes,
And
So
Very
yeah, I would
interesting.
like to add another thing what Professor Ghatak was saying. There is something very interesting which is happening right now in the country, and that is, unfolding of this national education policy, where we are actually talking about a 4-year degree at undergraduate level. And then we are saying that 1 year must be spent for doing research. And if we are really talking about that, that will mean that maybe we will have some kind of groups where these kinds of strategies can be implemented to get wonderful inputs for teaching itself. So I think country is getting ready for all those things. Maybe a platform like IAPT can really carry forward these kinds of messages, that these are the things which are possible, which can be implemented. And as you told, you prepare a lot of instructional materials, and we have been trying to float these ideas among our community also, that please come together. We are talking about competence building. How can that be done? Can that kind of idea be propagated at different levels? And because IEPT operates at school level, at undergraduate level, at university level, so we have a lot of opportunities to go ahead and talk to our community and do certain things. So I believe that there are lots of possibilities which we need to explore. Thank you.
yeah.
Most certainly.
Thank you.
Thank you.
Yeah, 1 minute. Thank you, Jaya. I have one question. You can suggest me actually? Can we use technology or simulation to support students' understanding in this concept?
I
Have you ever made use of something in your projects or somewhere in your studies?
So like in the current project that I'm talking about, I did not, but like the FED simulations that are available, those are really helpful, like incorporating those simulations in the classroom, or even for like there are different kinds of simulations, and like some people who are working on quantum tutorials in our group, even they have those simulations incorporated like in the tutorial. So like you just when you are learning certain concepts, you just go to the simulation, play with it, and come back and then try to answer those
Okay,
problems.
these
So that can
problems.
be really helpful, like
So you
in.
have worked on that also, right? So
Yeah.
maybe I'll ask you something in details later.
Sure.
Yeah.
Okay, sure.
Thank you for wonderful talk.
Thank you so much.
Thank you. I don't see any other raised hands. I have a question, Jaya. In the maybe if you can share your screen for the moment again. So
Yeah.
in the task that you gave with the second and the third one, where you had a 90-degree and a 60-degree thing, right?
Mm-hmm. Yeah.
Yeah. So did I understand correctly that no, maybe
The next one.
what exactly? So you gave this diagram to the students,
So
or
this diagram was not given, but
Mhm.
so if you see this y-axis, x-axis, and this yellow shaded thing,
Right?
this was given to student. This diagram was
Okay.
given.
Okay. And can you
Uh,
just show me the wording that you had used in the problem statement?
Here.
Right. Yeah. So you mean both planes are infinite, right?
Yeah. Um,
They, because I didn't see that. And so, no, I was just wondering. So you terminated both the planes at the origin, right?
yes. Yeah.
Whereas in your first task, I think you may have said that that's an infinite conducting plane, correct?
Yeah. For 90-degree one, right?
No, in the first one where you had only one, right?
Yeah,
The
that was
usual
it.
problem.
Yeah,
Ah.
I did say that
So,
it is
but
in.
in these cases also, you mean that the planes are infinite, right?
Yeah, we did not mention it here. Actually, we are considering it like semi-infinite here, but it should be like explicitly said.
So that's what I was wondering whether you're considering it semi-infinite or you also want, I mean, so I was wondering if you extended the planes, along, let's say, downwards and sideways, would that
Mhm.
have, do you think, would that have made them realize that the reflections will be on those things also, because they will see that, okay, now I have another plane and therefore I need to have another image there, etc. That's what I was just wondering. Or let's say when you go to the 90 degree, maybe that is easier to see. I was just wondering, I mean, whether you have thought about this, because I saw in the diagram. Sorry, somebody. Yeah. So I was wondering. So so you have said semi-infinite perpendicular planes, right?
Yeah, here I think we have explicitly said it is semi-infinite, but I think we did not say for the 60-degree problem what kind of.
Right. Yeah. So I was just wondering whether the students, I mean, whether, I mean, once the student places one image charge, let's say in the second quadrant, and then to realize that there will, I mean, that it would be, I mean, that another image will be formed just like with mirrors that we have, right? So whether making, so whether if you, I mean, did you probe whether they thought of that, whether, or because you said that they first thought that only one or two image charges will be enough, right? In this case?
Yeah, I think like they were thinking about how if they have two different scenarios, like if they have an infinite plane with a point charge and then another infinite plane with point charge, and they were thinking about two different situations, and then they added it together. So there was an evidence of that kind of thought process, and then they thought that because one charge is coming from here, one is coming from here, and then there should be two charges. So that kind of sense making was like observed in that scenario.
Right. No, this thought came to me because actually in our Olympiad program, we had once framed this question, and then we have used it in other programs also, where it's nothing to do with electrostatics, but simply with optics. I mean, mirrors at an angle, and we found that students often forget that unless they see the mirror right in front of the object, they forget that there'll be an image created by that mirror. So for example, in this case, that if you put something in the second quadrant, that it will have a image in the third quadrant also, because of this x-axis mirror. I'm talking of just plain mirrors here. That, but then once they draw the line on that side, then okay, now they can relate it better. So I was wondering whether that kind of scaffolding may also help. That because I mean, unless you understand what I'm saying, that unless the object is right in front of the mirror, like here, it is very clear that the two green things will create images, but that there will be an image in the third quadrant also that they often miss, and especially if it is at an angle and all that. So yeah, that was just a thought because we have seen this in a similar optics problem. Yeah.
Yeah, I think that could be interesting to like further see, like the way you are suggesting, maybe we can look more into how students think about that particular scenario. That can be like explored more.
Right.
But yeah, thank you for the suggestion.
Yeah.
That's a very interesting point, because what he has raised, so you can translate the entire thing to that two mirror problem. It would be the same.
Right.
There is one thing more. You know, what kind of exposure these students had when they came for doing these or solving these problems? I mean, did you give them some tutorial or something like that, where you explained what is the method of images, and then you allowed them to come forward and do the problems?
So all these tests or tutorials that we were doing, those were conducted after the class instruction. So once they got the lecture in the class, and after that we wanted to see how much problem solving skills they are developing, or like how we can provide support in problem solving. So they were familiar with the concept, they learned it in the class. And because I was doing interviews with like different students, advanced students, for this situation, there were some students who maybe learned the concept when they were in the course, like 1 year ago, 2 years ago. So there was some difference in when these students were present. But when we were implementing these things in the classroom, it was always done after the instructor has given instruction or lecture on this topic.
and you were not part of that lecture business as a teaching assistant or something like that?
So when we collected the quantitative data, I was just giving the test and tutorial, but I wasn't part of, like, as a TA, I just worked for that one class where I collected the data, but I did not teach anything, or I was not involved in that process of teaching.
Okay, thank you.
Thank you.
Thank you. Unless there are more questions, Sapna?
I
Yeah,
don't
someone.
think so. There are any other questions. I can't
There
see
is
anything
one.
in chat.
There is one from, I think, Kolahal.
Yeah. Yeah,
Okay.
so I'm sorry, actually, I could not raise the hand because I'm connected to my phone and it didn't
That's okay.
show up.
Just ask. Yeah.
Yeah,
Yeah.
right.
That's okay.
So I'm sorry, actually, I joined a bit late, but this is a very, very fascinating topic. And I mean, like many of us, we like this topic very much. So one thing that Jaya, you mentioned that, I mean, you have seen that nudging the student to a particular, I mean, checking up a few things sometimes helps. And just now what Anvesh just mentioned that some students in your class, they might have been familiar with the equivalent optics problem. So do you think that, I mean, say nudging the students, I mean, using a topic which is kind of known to them would be more helpful? I mean, basically they can develop based on their intuition. So this is a, I mean, sometimes this can be a very, I mean, obvious answer, but at the same time, sometimes there may be, you know, I mean, some tricks or certain points which are not exactly similar between two equivalent problems. So, what are your thoughts on this?
Yeah, thank you for the wonderful question. I think, like, I have observed this thing when I was looking at another tutorial, that sometimes it is good to like, as I talked about the transliteration of mathematics game, like sometimes it is good to use a concept that students have learned in different class and then implement it here when it relates. But I have also seen like in another, like when I was looking at Laplace equation tutorial, it sometimes, like, solving that problem is similar to having like quantum mechanics. If they are learning quantum mechanics, they have similar kind of situation there. And then for one of the students, I found that they were just using whatever they have learned, like whatever they have solved, they just used that whole concept here, but they did not think about, like, if they have to find what is the value of constant, they thought that, oh, when I was doing it in quantum mechanics, I had values as 1, 2, 3, 4, I will just use it instead of solving it. So sometimes it can be good, but sometimes it can be also harmful when they are not understanding or actually doing the thing, but they are just doing plug and check, or directly translating the concept without actually going through it. So again, like, asking them to think through the problem is more important, even if they are using the concept to different topics.
That's a very important point.
Yeah, right. Yeah.
Jaya, what Dr. Kalol mentioned is very important. I have found, for example, that understanding basic concepts in quantum mechanics, one can understand them by seeing the modes in waveguide theory. And those are much easier to understand, most easier to visualize. And this I've used myself and to great efficacy. This is another area of physics education that there are certain difficult topics. Understanding quantum mechanics for a BSc student is difficult. And if you tell them waveguide theory and show them experiments in quantization of modes and things like that, the equations are almost identical. And so, therefore, just as in the image problem here and the image problem in the two mirrors, as was mentioned by Dr. Majumdar, they are very similar. So maybe you can bring out topics like this that which can be taught here and there, and one can integrate, sort of couple them together, and make life easy for the teacher as well as for the student. Just a suggestion, but this was a very interesting point.
Yeah. Thank you. I think, yeah, we can, like, still, whenever we are teaching a topic, we can also ask them to think about what you have already learned. So that could definitely help if it is something which they are, like, thinking through. Yeah.
Yeah. Thank you.
Thank you.
So maybe we can now wrap up this session. Dr. Sharma?
Yeah, I think we don't have any question in the chat box also. So yeah, so thank you very much, Anvesh,
Yeah, let's
for chairing this
thank
session.
Jaya
Yes.
for a wonderful talk and answering all the questions. Thank you.
Yeah. Thank you, Jaya. So as we come to close of this lecture one of PER lecture series, so it's my privilege to extend a heartfelt vote of thanks. So today's session on students' sense making during physics problem solving has truly been thought provoking and very, very insightful, Jaya. The talk beautifully highlighted how physics problem is not merely reaching or arriving at the correct answer, but also understanding the whole process. So thank you very much for joining us today. I also thank Professor Anvesh Mazumdar for chairing this session very nicely. And thank you very much, Professor Aluwalia, Professor Ghatak, Professor Kuldeep Sharma for joining this lecture, one of lecture series. And I hope to see you in other lectures of this lecture series. Thank you very much. And with this, we close the today's session. And
Thank you.
with the hope that
Thank you.
I will see you all in the
Bye.
next lecture. Thank
Thank
you.
you.
And
Bye.
good night and good morning. Yeah. Yes.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you, everybody.
Thank you.
Thank you.